Hello geometers and seekers of truth. In this video we will discuss this theorem, and I'm gonna in the interest of time just skip over this proof for now, and perhaps we'll go back to it later. I'll add it as supplemental material, but it's very similar to the proof that we did regarding the two intersecting chords. Okay, so if two segments intersect like this outside of a circle, then the product of the lengths of one segment and its external part, so the product of the lengths of one segment and its external segment, and we have to be very careful how this is stated. So the product of the lengths of the secant segment, so that's EB, that's the whole thing, right, times its external segment, so that's just this part right here. So it's like this short segment times the whole thing. A lot of people make the mistake of taking the two smaller segments and multiplying them together. No, that's not the case. So it's EA, that's just the segment on the outside, multiplied by EB, which is the entire thing, okay, is equal to kind of the other analogous portion of it. So is equal to the whole thing, right, that's ED, right, multiplied by the external segment, which is EC, so this part right here. Okay, so the smaller part that's on the outside multiplied by the whole thing. All right, and I would just again, I'm not going to get into the proof of this. I'd like you to actually work on this on your own, but a hint for you is that if you make these connections here from there to there, and maybe from here to here, okay, there are some similar triangles that you can use and exploit in order to complete this proof. Okay, all right, so I'm going to actually pause and continue on to the next part, the last theorem that we have here, which is something we haven't proved yet. All right, so we're going to look at the third of the three theorems here, and this is the one that we haven't proved and we haven't really fully solved the example yet. And rather than looking at what the theorem says, I'm going to just kind of play with this picture a little bit and follow along kind of the same idea as what we've been using in the previous examples. Okay, so what I'm going to do is connect point A to point D, so AD, and then I'm also going to connect from A to C. Okay? And when I do this, some congruences come into mind. So if we look at this particular angle here, EAC, you see that it inscribes arc AC. Okay, so that arc, that light blue arc right there, is inscribed by that angle EAC. But that same arc is also inscribed by angle ADE. So like this red angle right here, right, it also inscribes that same blue arc, that light blue arc. So what that tells us then is that angle ADE is congruent to angle EAC, okay, because they both inscribe the same arc. All right, and if we go a step further, you can see that there are two triangles here. There's the smaller triangle EAC, this blue triangle right here, that also contains angle E, and then the bigger triangle EAD, that also contains angle E, right? So angle E is congruent to itself. It's effectively, it is a reflexive angle, okay? And that's enough for us to show that the two triangles are similar. So I'll just write this up. AEC, that's this angle here, is congruent to AED. And so that's enough for us to say that the two triangles are similar to each other. And we just have to be a little bit careful how we write it up. So the blue triangle, I'm going to go from E to A to C. So triangle EAC is similar to, and the red triangle, well, I have to do kind of the same thing. E is congruent to itself, so I have to start with E. Now, the next thing in my blue triangle is A, so it's this one with the congruent mark. So that has to match up with D, because that also has the congruent mark here. So E, D, and then A. Okay? And so they're congruent, they're similar, excuse me, by the angle-angle postulate. And again, with this in mind, we can put together some similarity or proportional statement. EC in the first triangle matches up with EA in the second triangle. So I can write that up. EC over EA is equal to, and then in the first triangle, EA, right, so EA in the first triangle matches up with ED in the second triangle. All right. So that's a statement of proportionality. And now if you look at this, if we cross multiply once again, we have EA times EA, that gives us EA squared, and then ED times EC, so that gives us the right side of this. Okay, so namely that when you have a line segment right here that's tangent to the circle, it's that segment squared is equal to the short segment, that's EC, multiplied by the whole thing. Okay, so that's what this theorem is really saying, is that this length here squared is equal to EC times ED. All right, so hopefully you get a sense of these particular types of theorems, how to prove them, how to set them up. They all revolve around similar triangles, and then from the similar triangles, we get a proportionality statement, and then we can get kind of an expanded statement like this. All right, and then in the last part here, I'll show you some examples of these problems. As always, thank you for watching, and have a wonderful day.